Welcome to your first hands-on journey into quantum circuits. In this session, we'll explore how quantum circuits work and how quantum gates work, how measurement collapses states, and how we can construct meaningful circuits. You'll build your first Bell state, compare quantum randomness with classical behavior, create custom superpositions, and experiment with two-qubit entanglement, all key foundations for understanding real quantum computing. Let's compare classical and quantum programming. Classical programming uses deterministic logic. Let's say we have a program if x is greater than 0, let's return 1, whereas if x is not less than 0, greater than 0, let's return 0. So if x is 10, it will return 1, and if x is minus 1, it will return 0. But whereas coming to quantum programming, that follows this flow. We start with the quantum state side, apply gates, then measure to get the probabilistic output. A real example is that the quantum random number generator. We start with basis state 0, apply a Hardeman gate, then measure to get a true random bit, not pseudo-random like classical computers. Why do circuits matter? They provide model quantum algorithms and also describe quantum evolutions. They also map to physical hardware. Whereas the key concepts for quantum gates are unitary matrices, circular depth is nothing but the time complexity, and number of qubits used will determine the space complexity. Now let's look at qubit math using block sphere. We have ket 0 is 1 0, ket 1 as 0 1, plus ket is ket 0 plus ket 1 over root 2, ket minus is ket 0 minus ket 1 over root 2. Here are the essential gates with their matrix representation, Hardeman and Pauli X. For two qubit gates, C0 is this, and C0 transform these basis states in this. We only have change for ket 10 and ket 11. While coming to measurement, it follows Bond rule. Let's say for quantum state, 0.8 ket 0, 0.6 ket 1, probability for measuring 0 is 64%, probability of measuring 1 is 36%. Our first circuit creates a Bell state for quantum entanglement. The goal is to create this state. Here's the step-by-step evolution. We start with the initial state, get 0, 0. After applying Hardeman gate, we'll get this quantum state. Further, after applying C0 gate, we'll get the required state. Let's look at the implementation. The penny-lane implementation imports penny-lane as QML and NumPy as NP. We create a device with default qubit and two wires. The QML QNode decorator defines our Bell state function. Inside, we apply Hardeman to wire 0 to create superposition, C0 to wire 0, 1 to create entanglement, and then we'll return QML state. To execute and analyze, we call Bell state and then the probabilities of calculate probabilities, and then we'll print the probabilities of base state 0 0 and 1 1. After this is the output, the Bell state is this, and the probabilities of base states are 0 0.5 and 0 0.5. This is the circuit diagram. Here we are first applying Hardeman gate and then C0 gate. Let's compare quantum versus classical randomness. For classical pseudo-random generation in Python, we import random and create results as a list comprehension. This uses a deterministic algorithm called linear congruent generator. It is predictable if you know the seed. For quantum true random generation with PennyLane, we import PennyLane as QML and create a device, quantum device, with one wire, default qubit with one wire. The QML.QNode decorator defines quantum coin function in which we apply quantum Hardeman gate to wire 0 and return the sample. This gives true randomness from quantum mechanics. For statistical analysis, we calculate classical mean, which is equals to just mean of the results. Approximately, we'll get zero point 0.5, and the quantum mean also with the mean of all the quantum results, approximately zero point 0.5. But quantum passes all the randomness tests. See here, we got 0.511 in classical, and quantum mean also 0.504. Now, circuit variations include basic version with get 0 through Harman to measurement, biased version with get 0 through RY gate to measurement. We are applying RY gate on theta, which controls bias. Multi-bit version also with parallel get 0 through Harman is measurement for each qubit. Let's explore creating custom superposition states with different gate combinations. We have basic superposition state get plus, that is get 0 plus get 1 over root 2. Here we have probability of both 0 and 1 as 50%. Get minus, where is get 0 minus get 1 over root 2. Here also the probabilities remain equal and 50%. Get plus I, the formula is different, whereas the probabilities are 50% and minus get I. We can achieve these states with the gate sequences. Plus can be achieved by applying Hadamard gate on 0. Minus can be achieved first by flipping the get 0 to get 1 and then applying Hadamard. Plus I can be achieved by applying Hadamard and S gate on get 0. Whereas minus I can be achieved by applying Hadamard gate and S dagger. We have RY gate which flips the position by an angle theta on across y-axis. For bias superposition with custom probabilities, Ry of theta creates cos theta by 2 get 0 plus sin theta by 2 get 1. Where theta is pi by 6, the probabilities become 75% for 0 and 25 for 1. When theta is pi by 3, the probabilities become 25% for 0, 75% for 1. When theta is pi by 2, the probabilities become equal, that is 50%. The penny lane implementation, firstly, we'll import penny lane and NumPy, and then we'll create a quantum environment with default qubit and one wire, and then we define functions. First function, create plus state. We know that plus state can be created after applying Hadamard gate on get 0, and then get minus. Minus state can be created after applying poly X gate, which will flip the get 0 to get 1, and then applying Hadamard gate, which will give us get minus, and then creating plus I state. We know that plus I state can be created after applying Hadamard gate and then S gate. So after applying Hadamard gate, 0 will become get plus, and then applying S gate, it will become plus I. And then we are creating bias states, which will take in an input theta and apply Ry with theta value. We are creating plus state, minus state, and plus I state, and then creating the probability 75 for 0, 25% for get 1 using pi by 3 angle, pi by 6 angle, and then 25 for get 0 and 75 for get 1 using pi by 3 angle, and then printing the results. If you can see, here are the circuit diagrams for the following states and then the probabilities. We are not printing the probabilities but matrices. Here both are equal, so 50% for both. Here also 50% for both get 0 and get 1. Whereas coming to plus I, here also we have get 0 0 is also 50% and get 1 1 has 50%. And for probability 75, 25 and 25, 75, these are the values. Now let's discuss about two qubits entangled state. Bell states are four maximally entangled two-qubit states that form a complete orthonormal basis. These states are central in quantum communication and teleportation. These are the states and respective formulas. They represent the perfect quantum correlations. If one qubit is measured, the state of other is instantly determined. Now, gate sequences to create Bell states. The standard approach uses a Hadamard gate on qubit 0 followed by C0 gate. Additional gates modify the phase or bit values. We have Hadamard gate and C0 gate. Additional gates are used to modify the phase or bit values. We also have alternate sequences. Quantum gates can often be reordered. Apply Z gate before C naught. Here we applied first C naught gate and then Z. Here we are applying Z gate and then C naught. So we can apply different orders to get different combination and different sequences. These are useful for optimizing on different hardware. We also have partial entanglement. To control entanglement, we use rotation gates. Ry of theta on qubit 0 plus C naught gives cos theta by 2 basis state 0 plus sin theta by 2 on basis state 1 1. When theta is pi by 4, we say that it's a weak entanglement. When pi by 2, maximum entanglement is possible. And 3 pi by 4 is also weak entanglement because it has opposite bias. We begin by setting a quantum simulator which uses two qubits. This will allow us to create and observe entangled two qubit states. Firstly, we are creating Bell 5 plus state. Firstly, we'll apply Hadamard to create superposition and then C0 gate which will entangle qubit 0 with qubit 1. This will result in cutoff 5 plus state. Then we are trying to create 5 minus. Firstly, we'll apply Hadamard gate and then C0 gate on qubit 0 with qubit 1. The result will be, and then again we have to apply Z gate to qubit 1 to flip the phase of cutoff 1 1. We have got 1 1 right after applying Hadamard and C0 gate. To flip the phase, we'll apply Z gate, which will give us phi of minus. And then we'll try to create psi plus. Here we need to apply Hadamard gate and then C0 and apply poly X which will flip the target. So we'll get this equation. Firstly we are applying on 0 0. We are applying Hadamard to get 0 0 plus 1 0 by root 2 and then applying C0 gate we'll get cutoff 1 1 and then applying phi naught. This will be flipped to cutoff 1 1 right. So that will be cutoff. This is after applying C0. After applying for polygate, we'll get cutoff 0 1 plus 1 0 over root 2. And then for psi minus, we are applying Hadamard gate, C0 gate, X gate. We are just applying Z gate extra. Finally, this is for partial entanglement. We are applying pi by 4 for weak partial entanglement and pi by 2 for strong partial entanglement. And then printing the states. If we observe the output, these are the matrices and for after applying weak entanglement and maximum entanglement. This is when theta is pi by 4 and pi by 2. This for weak and for maximum we'll apply pi by 2. Let's quickly review what we have covered. The Hadamard gate creates our basic superposition that is plus state. That gives us equal probabilities but with positive phase. For the minus state, we use X gate and then Hadamard gate, which flips the phase. So same probabilities but opposite phase. Adding the S gate after Hadamard gate gives us plus I with imaginary coefficients. These phase relationships are crucial for quantum interference. Moving on to 2 qubits. All 4 Bell states start with Hadamard gate and then CNOT gate. This is the foundation pattern. And then for phi of plus, we have Hadamard and CNOT gate. This is the basic entangled state. And phi of minus, we need to add Z gate for phase flip from plus to minus. And then we add X gate for bit flip of psi plus. Same as for what we did from phi plus to phi minus. Here also we'll add Z gate to flip from psi plus to psi minus. Remember, C0 creates the entanglement. Additional gates modify the phase and bit relationships. Okay, now we have gate order independence. That is, we can apply C0 first and then Z, or Z first and C0. Because of their commutational properties, we can apply C0 and Z anytime. And then considering applying C0 followed by Z on the target qubit versus Z followed C0, the values will be same. Here the order is, we have two orders, C0 and then Z, Z and then C0. This works because of their commutation relation. Today, we took our first practical steps into quantum computing. From building basic circuits and exploring quantum gates to creating entangled states and comparing quantum versus classical randomness, we have seen how quantum systems behave in ways classical ones simply can't. This hands on experience sets the foundation for deeper exploration into powerful quantum algorithms.
Quantum computing videos.